Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI-generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we will explore OpenMP offloading on multiple GPUs, applying OpenMP for multi-GPU parallel computing. I have created a new directory called GPU Parallel OpenMP in the work folder on Saga. We'll use this directory to submit job scripts and explore multi-GPU parallel computing on the A-100 nodes. I have copied the testing GPU Python script and the job script from our previous video into this new directory. Additionally, there's a Fortran program for multi-GPU parallel computing in this directory. I have used file ending 4 to match the Fortran program from our previous video, as it uses the same OpenMP offloading. Let us explore the Fortran program for multi-GPU parallel computing. First, we need to include the OpenMP library, as we have done before. Then, we'll set the matrix dimension parameter n to 16384, just like in our previous video. I have added a new parameter to the program to set the number of GPUs we will use. Since we are using multi-threading with OpenMP, the number of GPUs is limited to those available on a single node. On the A100 nodes, we can use up to 4 GPUs, as each node has 4 GPUs. In the program, we have defined some new variables for multi-GPU parallel computing. We will explain the purpose of these variables as we go through the program. The A100 nodes have 32 CPU cores. We can use 8 CPU cores per GPU while keeping the billing factor at 8. Previously, on the Fram and Betsy Linux clusters, we set the number of threads using the OMP, num, threads, variable in the executing command. Here, we'll set the number of threads directly in the Fortran program by calling a subroutine from the OpenMP library. The number of threads is set to match the number of CPU cores used in the initialization loop, since this loop will not be offloaded to the GPUs. We'll include the OpenMP directive parallel do in the initialization loop, so it executes in parallel on the CPU cores. The reduced dimension, Rn, will be calculated as the matrix dimension, n, divided by the number of GPUs, n GPU, used by the program. Next, we'll set the number of threads to match the number of GPUs by calling the same subroutine from the OpenMP library. The number of threads is adjusted to correspond with the number of GPUs, since the matrix multiplication loop will be offloaded to these GPUs. We'll begin multi-GPU offloading using the parallel directive with the private option. The private option ensures that the variables thread number and offset are unique to each thread. The thread number is obtained using a function from the OpenMP library and acts as an identifier for each thread. We need to attach each thread to one GPU device. This means that the computations performed by a thread will be offloaded to one GPU. Using multiple threads will enable multi-GPU parallel computing. To attach each thread to a GPU, we'll call a subroutine from the OpenMP library. We use the variable thread number when calling this subroutine, ensuring that one thread is attached to one GPU. The offset variable is calculated as the thread number multiplied by the reduced dimension, Rn. We will use both offset and reduced dimension in the J loop for matrix multiplication. We'll use the same OpenMP target directives for offloading as in our previous video. Note the loop order of J, I, K, and that the J and I loops are collapsed. Since multiple threads or GPUs will perform the matrix multiplication, we need to divide the J loop workload among them. We do this using the offset and reduced dimension, Rn, variables in the J loop. This ensures that each thread uses different J values, preventing them from performing identical computations. For the K and I loops, we'll only use the matrix dimension variable n. We conclude the multi-GPU offloading using the end parallel directive. After that, the program continues as before with the output of the C matrix. In the testing Python script, we'll use the A-100 GPUs because OpenMP offloading is only supported on A-100 GPUs. The offloading is set to OpenMP, indicating OpenMP offloading with multi-threading for multi-GPU parallel computing. The file ending is 4, and the matrix dimension is set to 16384. The CPU billing is set to 16 because we'll use 2 GPUs in our parallel computing. The performance will be calculated as before. We are implementing compilation optimizations for the A-100 GPUs and have added the option to obtain details on the OpenMP optimization using the MP option. The compilation option for OpenMP offloading is used. We will execute the testing process as a batch job using this job script. The partition option guarantees that the job will be executed on one of the A-100 nodes. The job script requests 16 CPU cores and 2 GPUs. We will be placed in the development queue and use recommended settings for error handling. We need to load the latest NV Fortran compiler and switch to an environment that supports the AMD architecture. Once these specifications are set, the job script can execute the testing GPU Python script. We can now use the sbatch command to submit this job to the Slurm workload manager, and we see that the job has been assigned the number 11802534. Using the sq command, short for show queue, we can see that our job has been running for 2 seconds. After some time, we use the sq command again and observe that the job has completed. We can use the ll command to check if the job has produced the Slurm output file with the job number 11802534. We see that the Slurm output file has been generated, and we can view it using the Emacs editor. In the Slurm output file, we see that the test was conducted on the GPU 12.2 node. The file also contains some warnings and notes, which we can remove to enhance clarity. The first output is generated by the command that switches to an environment supporting the AMD architecture. The testing Python script outputs the compilation command, and we observe that the minfo and mp options do not produce much information on compiler optimization during parallel OpenMP offloading. The wall time for multi-GPU parallel computing with 2 GPUs is approximately 14 seconds, achieving a performance of about 39 gigaflops. Previously, using one GPU, the wall time was about 22 seconds, resulting in a speedup of approximately 1.6 when upgrading from 1 to 2 GPUs. In our upcoming video, we'll demonstrate how to confirm the accuracy of our multi-GPU parallel computing method for matrix multiplication. We will introduce a Fortran program to calculate if there is some error in the multi-GPU parallel computing method presented in this video. I am looking forward to the next video, wishing you all happy computing in the meantime.